Hello, and sorry I have to be out today. Hopefully this video will not only to help you to learn what we need you to learn today, but you'll be able to go back to it and learn more if you need to. First of all, if you don't have your periodic table out with your notes, it's a good idea to get both of those things out right now because I'm going to be referring to the periodic table a lot during this. The first thing we need to do is remember some facts about the periodic table. Remember that all the elements are in order of atomic number. They contain all the same electrons that came before them plus one. So for example, if you look on your periodic table and you see potassium, potassium has the exact same electrons as argon plus one more electron. So basically what I'm saying is when I'm talking about these quantum numbers today, you have to remember when I talk about the quantum number for potassium, I'm not just talking about potassium's one electron because potassium has a lot more than one electron. So there are exceptions to this, but we're going to visit those later. So in the following descriptions, we're going to be referring to just the last electron that's been added to the element, right? So in potassium, we're going to be talking about the 19th electron because it's number 19 on the periodic table. And we know that potassium has 18 other electrons, but we'll be talking about its last electron. Quantum numbers. So I've been using this word in class, quantum theory. We learned what a quanta was, but quantum numbers are a little bit tricky. They're nothing like anything you've ever done before. All electrons, and again, we're talking about the last electron, are described by four quantum numbers. N is the principal energy level. As N increases, the energy in the distance from the nucleus increases. L is the energy sublevel, shape of the orbital as well. M sub L, and this should be a sub L down there, it should be a big M and a small L, but it didn't print quite right, is the actual orbital, or the direction of the orbital in space. M, and I say sub S, is the electron spin. We're going to go through each and every one of these, but basically a quantum number is like this. It's an address for an electron. We talked about orbitals and how they look kind of funky in space, but each one of those electrons, every single electron on the periodic table has this address. So each one of the four quantum numbers describes something more specific. N being the most general, like we live in Troy, Michigan, and L being a little bit more specific. Troy is the city we live in. M sub L being like our address, and M sub S saying exactly who you are that lives at your address. So back to the Bohr model. Just as Bohr proposed, electrons exist in specific energy levels. This is where we're going to get the main principal energy level. These energy levels can be found using your periodic table. I'd like you to take a look at the left-hand side of your periodic table. You're going to be seeing 7 period numbers. So for the main group elements, they are the period numbers. So these are what we call the S block, 1, 2, 3, 4, 5, 6, 7. And this is the P block of your periodic table. Now you'll notice here this entire part is kind of missing because we're going to talk about that in just a second. The transition metals, which is that part I just drew in green, the energy level is the period minus 1. For the inner transition metals, the energy level is the period minus 2. So this probably doesn't make sense yet, but we'll take a look at it. I like you to remember energy levels, and that's how you remember that it's the N quantum number that refers to the energy level. This diagram really sums that all up the best. We were just talking about the energy levels. So here are the main group elements. Here I'm circling in red. Main group elements have the period numbers as the energy level. So you can see period 1, 2, 3, 4, 5, 6, and 7. The transition metals that I'm circling here in blue, remember I said it was the period -1. So right here I'm in the 4th period, but this transition metal is the 3rd energy level. The F block, or down here, the lanthanides and actinides, it says that it's the principal energy level, it's the period -2. Now this can be a little bit confusing, but remember these fit up in here, and if you kind of remember that, it looks like this right here should be number 6, but it's actually number 4. Many people kind of forget about that -2 thing, and they just remember that this row is 4 and this row is 5. The next quantum number is the sublevel, and the sublevel is the shape, and you're going to hear me refer to it as mostly the shape of the orbital. So there are 4 sublevels, S, P, D, and F. These 4 sublevels are here to stay. We're going to talk about them a lot. So you're going to hear me talk about the S block of the periodic table, the P block of the periodic table, the D block, and the F block of the periodic table. A good way to remember this is sublevel. So the L quantum number represents the sublevel. So right now, it is a great idea to just label a periodic table, commit this to memory, S, P, D, and F. So the first sublevel is the spherical shaped sublevel. This one's really easy because the letter S starts with an S for spherical shaped. This is the one that we looked at when we looked at hydrogen's electron cloud. The quantum number is actually going to equal 0. So this says L equals 0. It starts to count in order, it just starts with 0, but you can remember that the number 0 is a sphere. The second sublevel is a P sublevel. I think P sounds kind of like propeller shaped, so that's why I kind of came up with this. If you want to remember, some people call this the dumbbell shape, just in case you want to know, but I think it kind of looks like a propeller shape. The quantum number for this is 1. The third sublevel is the D sublevel. I call this the double dumbbell shape. And the double dumbbell shape looks like this. Again, quantum number L equals 2. So basically you're matching these letters up with numbers. And the last sublevel is F. And F, remember, I just said it was a frenzy of electrons. It is too complex to visualize. I'm never going to be asking you to be drawing, these strange shapes here. The quantum number is L equals 3. So just to review, just to make sure you're understanding this, S has a quantum number L equals 0, P equals 1, D equals 2, and F is 3. And those will become important when we do quantum numbers. Now the next quantum number has to do with the orbital. Remember, each orbital can hold 2 electrons. We kind of talked about that already. The real world is 3D, so you have to usually visualize these orbitals as, instead of just being perhaps an X and a Y axis, it's better to think of it as the, X, Y, and Z axes. And they kind of come out at the paper at you, that Z axis. So we need to designate the direction of the orbital and the direction it takes up in space. The next quantum number is a little bit tricky. It is the magnetic quantum number, or M, and that should again be sub L. It tells us where the orbital is relative to the nucleus. You've got to think about that 3D world. So you're looking here, these are p orbitals, by the way, you can tell because they're propeller shaped. And you can see that this p orbital right here is sticking out at us. This one is right parallel with the page in that direction, and this one's parallel with the page in that direction. That gives us 3 different orientations or 3 different quantum numbers that the p orbitals can exist. In this case, it's pretty easy to count them. Remember that the p orbital equals 1 when we were talking about sublevels? Well, you just take that and now it's -1, and you would go through 0 to whatever the +1 is. Now, in the case of the p orbital, that's all we have is -1, 0, and +1. But you can see down here with these other subshells, the S subshell, all you have is 0. It is the only orientation. When you think about it, a ball can't come out of the screen at you or go into the screen. It only has one orientation. The p sublevel has 3 different magnetic quantum numbers or orientations. Those are the ones that I'm showing you here. The d sublevel, remember d equals 2. So when you look here at the d sublevel, it has -2, -1, 0, 1, 2. And then the f sublevel does the same thing. It starts at -3, -2, 1, 0, +1, +3. This doesn't really make sense to you, probably what these numbers mean yet, but hopefully the more we do this, it'll make a little bit more sense. These are the shapes that we're going for. I'm never going to have you memorize this table or these shapes, what they are. We'll leave that for future. But as you can see here, here's the S with its 1 orientation. Here's P with its 3 orientations. There's D with its 5 and F with its 7 orientations. So those are the shapes that you can start to think about, even though you don't have to have those memorized. The last quantum number is the spin. And the spin, again, this should say m sub s. The spin is the spin of the electron. We can think of electrons as either spinning up or down. So one electron spins up, the other electron spins down. Because remember, each orbital can hold 2 electrons. So if you've got a very simple, let's think about a spherical shaped orbital with its 2 electrons, somewhere in there you have one electron spinning up and you have another electron spinning down. So one has a magnetic quantum number of +1, that's the one that's spinning up, and one has a magnetic quantum number of -1, that's the one that's spinning down. Now, so people don't confuse it with the other quantum numbers, for some reason they've chose to designate it as 1/2 for both of these. So instead of being a +1, it's actually a +1/2 and a -1/2. And I'm sorry if you're totally confused, but I promise it's going to come together soon. So let's do a little bit of practice. You need to get out your periodic table and find germanium. Germanium is number 32 on the periodic table. All right? Germanium is located in the P block of the periodic table. That's probably the first thing that you should notice. All right, I'm over in the P block of the periodic table. That's where I like to start. So P block, remember, is number 1. So that gives me my L quantum number. The second place I like to go is the N. So because I'm in the P block, I simply use the period number. So the period number, remember the numbers on the left-hand side of the periodic table, the period number is 4, which gives me an N value of 4. Now I promise that this probably would be the most confusing quantum number right here, m sub L. If you look at the P block, you can see that there are 6 total electrons available in the P block. And remember, I told you that P can have 3 orientations. It can orient this way, it can orient this way, or it can kind of stick out of the screen. So if you look at this, you can see this electron spins up, this one spins up, and this one spins up in this direction, and this direction. Then the second half of the block, this electron spins down, this one spins down, and this one spins down. Again, in this orientation, in this orientation, in this orientation. So germanium is going to, we're going to count right through. Germanium is going to be located right here at number 0. -1, 0, 1. And then it starts over. -1, 0, 1. So germanium and bromine have almost the exact same address. You can see everything about germanium and bromine are exactly the same. N equals 4, L equals 1, M sub L equals 0. The only difference is the spin. Germanium spins up and bromine spins down. The next example, what are the 4 quantum numbers for the last electron? And I make a point here to say the last electron. Sometimes it'll just say the 4 quantum numbers for sodium. Find sodium on your periodic table. It's number 11. And like I said, the first place you want to look is the fact that it's in the S block. Since it's in the S block of the periodic table, L equals 0. Remember, spheres are circles and 0 looks like a circle. So the next place we go is what is its principal energy level. Again, it's a main group element. Because it's a main group element, it's easy. It's in the 3rd period, so N equals 3. The M sub L is actually really easy for the S block too. The S block only has one orientation. Don't forget, it's a sphere shape. It can only have one orientation. So M sub L equals that one orientation, which is 0. The last one is the spin. The first half of the blocks always spin up. The second half of the blocks always spin down. If you remember back to the previous example, the P group spins up, 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 and then down, down, down. So in the case of sodium, sodium is in the first half of the block, so it has a magnetic spin of up. Here would be a pretty complicated one. This is palladium. Palladium is number 46 on the periodic table, and it is in the D block. So the first thing I want to do is figure out my block. Like I said, it's in that D block of the periodic table. So the D block is actually number 2. Then I want to move to my principal energy level. Remember, principal energy level is the period number for main group elements. But in this case, this is not a main group element. This is a transition metal. So it's actually going to be the period number -1. And in this case, it's in period 6, or I'm sorry, in period 5, so N equals 4. The M sub L is very tricky. The M sub L is the magnetic orientation. You're just going to have to kind of trust me with this. The first half of the block, all the way to here, counts -2, -1, 0, 1, 2. This is every single time, so this doesn't change. You can label that for your D block every single time. The second half of the block all spins down, so it starts -2, -1, 0, 1, 2. Palladium is here in the second half of the block, so it's definitely going to be spinning down. So that's why we have a spin of a -1/2. That means down. The M sub L, you've got to count -2, -1, 0, 1, 2. It starts over again, -2, -1, 0, 1, 2. So palladium falls right there. Palladium is in an orbital with niobium. Palladium and niobium share an orbital together. They have the same N, the same L, the same M sub L. It's just that palladium has an electron that's spinning down, while niobium has an electron that's spinning up. Last example here. Praseodymium, kind of an odd one there. This is number 59 on your periodic table. Couldn't resist doing an F block element here. So number 59 is down in the F block. F has a quantum number of 3. So L for Praosinium is 3. The next place you want to go is the principal energy level. Now, it is technically, and remember, you can think about the inner transition metals as being part of the big periodic table. And technically, it is in the 6th period, even though people rarely think of that. So you would think 6 minus 2 equals 4, but a lot of people just remember that the lanthanide and actinide series starts with 4 and 5. So principal energy level is 4. M sub L and M sub S, remember we're going to do this thing where we're going to look at the block. Now this block has 7 elements right here that are all spinning up. And then it has 7 elements right here that are all spinning down. And it counts -4, -3, -2, -1, 0, 1, 2, 3. Right here, it starts over again, -3, -2, -1, 0, 1, 2, 3. So our M sub S is in the first half of the block. That's why it's spinning up. It has an up spin, which gives me a positive number. That's that positive 1/2. And that's because it's in the first half of the block. M sub L, I don't know why, this always is the trickiest number. You're just counting -4, -3, and in this case, it's, I'm sorry, not -4. Sorry, I wasn't reading that correctly. -3, -2, and so that's why this is going to be -2 here. That's what you're going to get for that one. So these are the 4 quantum numbers for that one. Now, I usually put this up here and I have it labeled to help or to totally confuse you. It gives you kind of a layout of principal quantum numbers, sublevels, number of orbitals per sublevels, number of electrons per sublevels, and then how many electrons per main energy level. Some kids find this really helpful, others find it really confusing. Hopefully you learned a little bit today, and do your homework today. You're going to be able to help each other and make some sense of this. I will see you tomorrow. Have a good day.